Good morning, Honors Algebra 2. This is Mr. Kim. Today, I'm going to go over the polynomial test review with you guys. The packet I've sent you yesterday in a PDF format, so I'm hoping that you actually had a chance to actually work on this just a little bit. It will be very similar to the one you see here. I'm not going to change it too much, but you need to have a solid understanding of how the zeros are sketched, the end behaviors, and all that stuff. Now, given the fact that probably if you guys needed just a little bit more time to kind of review, you can take this video and watch it over maybe today and tomorrow and just kind of study over this yourself, because it's really going to be very similar to the one you see here. And we'll take the test on Friday instead. I will just give a little bit of a day delay just to give you guys a little bit of a buffer to help you guys study over this and ask me questions for tomorrow and things like that. Okay. All right. So for this particular test or test review, for a graph question, if I give it to you like this, the one thing that you must remember is the end behavior as well as the multiplicity. Now, I see that there's three multiplicities here, here, and here, where it seems like it's bouncing off here and it's bouncing off here. So I'm going to write ×2, indicating that there's multiplicity of 2 there. And there's a multiplicity of 3 in the middle, indicating that it's actually happening 3 times. So if someone makes a claim that the above function is as following, I like what this particular person did with the x minus 3 and x plus 1 squared, because it is indeed x minus 3 and it has to happen twice. This is indeed x plus 1 and it indeed happens twice, but the problem exists right here. Yes, it does go through, but it goes through in a squiggly manner. So that means that this actually has to change into an x to the power of 3, x plus 1 squared, x minus 3 squared. Now, for the end behaviors, this is obviously, this will be the x to the 5th function. It's an odd. But if you take a look at the end behaviors, it goes down and then it goes up, which means as x approaches negative infinity, y approaches negative. As x approaches positive infinity, y approaches positive. The only way that this is going to happen if your leading coefficient is actually positive. So this actually has to turn into a positive x cubed rather than saying a negative x in the beginning like this. So that should fix up all the problems. So there were 2 mistakes. Writing as a cubic and then making sure that the front leading coefficient is actually positive. So do you agree with the answer? Obviously no. Why or why not? You can say of all the things I've stated above right here with the multiplicity of 3 and having the end behaviors, making sure that it's the leading coefficient is positive. So fixing it will be that. Write the following function in factored form. So this one, let's go over this. The zeros I need to identify first. So it seems like it's x plus 4, x plus 1, x minus 2, and then x minus 5. Okay, so I have all that. And now the only thing I really have to worry about is this 2. And then I gave you this 80 as sort of an experimental question. First, we should all agree that that should be squared because it's x minus 2 squared. Now, the one thing that you need to definitely check for is the end behaviors for this. I have x to the power of 5 here. That should be the leading term if you were to actually FOIL this out. Now, the end behavior is x negative infinity, y approaches positive infinity, x approaches positive infinity, y approaches negative infinity, which means I have to have a negative sign in front of that x to the 5th because it's got to be negative in an odd power degree, odd powered function in order to have a shape that looks like this. The reason why I pointed out 80 was because if you take a look at all of these numbers from here, 4, 1, -2, -5, and then this obviously has to be squared. 4 times 1 times 2 squared times -5, that actually gives you -80. Along with this negative sign in front of it, this actually makes it a positive 80. That's why the y-intercept is at positive 80. You just multiply the very last numbers along with the exponents and the leading coefficient, if there are any, to get that y-intercept value. All right, so now let's go over to number 2. Number 2 says g of x is at 10x to the power of 3 plus 29x squared minus 41x plus 12. Using your calculator, compute g of 5. All right, so I am just going to use our calculator here. Just going to pull it up on the side. Okay, so I am going to store 2 into the x. and then 10x to the power of 3 plus 29x squared minus 41x plus 12. All right, so that becomes 126, I believe. Do we have a 0 at x equals 5? That's definitely a no, because the remainder is not equal to 0. Our remainder is actually 126. Therefore, this is not one of the factors or one of the zeros. Use the remainder theorem to calculate a rational zero for the function above. This means I actually need to find the zeros based on the factors of 12, the very last number. It could be 1, 2, 3, 4, 6, or 12, or negative versions of those. But remember, the very first thing that we're always going to plug in is 1, positive 1 to the x. And then we're going to plug it in, away, negative x in there. Okay, that doesn't work. So let's plug in 2 in there and see if this works. All right, 2 doesn't work. Then what about negative 2? Does that work? Nope. So let's plug in 3. I'm plugging in 3. Oh, I should copy and paste that. All right, so 3 doesn't work. I'm going to plug in negative 3 and see if that works. All right, so that doesn't work either. What's next? 4, positive 4, store into the x. And then I'm going to plug this into the equation, see what happens. 952. All right, seems like I am never going to get my head around this one. So, oh, there we go. So I got negative 4 as one of my zeros. Finally, I did all this trial and error with going for fishing for these zeros, and I finally found one. So that means that negative 4 being one of my zeros, I can actually use my synthetic division with this. 10, 29, negative 41, and positive 12. That's what I'm going to use. Bring down the 10, negative 40, negative 11, 44, 3, negative 12, and 0. That becomes 10x squared minus 11x plus 3. And for those of you who noticed that this can be factored using the AC method, this is 30. And the two numbers that multiplies to 30 and asks to give a negative 11 is negative 5 and negative 6. So 10x squared minus 5x minus 6x plus 3. Factor out the 5x, we get 2x minus 1. Factor out the minus 3, we get 2x minus 1. So we get 5x minus 3, 2x minus 1. Guys, I'm not going over too much in detail. Again, this is just a factored form. Getting the zeros from the quadratic should be very simple. To calculate the zeros, so the zeros will be at negative 4, 3 over 5, and 1 over 2. Yes, I made this purposefully difficult, but for the test, I'm going to make it all integer values so that I just want to test to see if you know how to use this remainders theorem to get the zeros and factor accordingly afterwards. All right, so we found the zeros and we're sketching the function below. We have 10x cubed as our leading term, which means our end behaviors will go down here and will go up there. X approaching negative infinity, y approaches negative infinity. X approaches positive infinity, y approaches positive infinity there. So we have negative 4, positive 0.6 would be somewhere over here, and 0.5, which is about halfway there. So the graph might be a little bit tricky to graph, but here's what's going to happen. First, I am going to also plot the y-intercept of being at positive 12, somewhere over there. And now here's how it's going to look like. So it's going to hit that 0, hit that y-intercept, hit that 0, and then it's going to go back up. It's got to hit those two zeros at 1/2 and 0.6. I know that they're relatively very close to one another, but you have to do your best in picking those 2 points between 0 and 1, and then you will just sketch accordingly, matching with the end behaviors. So everything should be good from that point onwards. All right, so solving completely for the zeros. So now I have the divided by the divisor x minus 1 of using the long division, it says. So I'm going to do 6x cubed minus 17x squared plus 4x plus 12 divided by x minus 2. So 6x squared should come to the top, 6x cubed minus 12x squared. Then this becomes 5x squared because we're subtracting them. Bring down the plus 4x. I'm sorry, that's negative 5x squared. So we're going to have a 5x here, negative 5x squared plus 10x, because we're going to be multiplying those two to get the 10x right there. Then we're going to subtract everything and negative 6x, bring down the plus 12. Then the only thing that's left to do is put the minus 6. Minus 6x plus 12, because that's negative 2 times negative 6. Everything cancels out. So we have a remainder of 0, which means I have 6x squared minus 5x minus 6 that I need to factor out completely. Now this is another AC method. So I'm just going to show you by using the AC method here. AC is negative 36, two numbers and multiplies to negative 36, but adds to give you negative 5 is negative 9 and positive 4. By the way, I'm getting negative 36 because 8 times 6 times negative 6 is negative 36. So 6x squared minus 9x plus 4x minus 6. Draw that wall, factor it out. X minus 3 or 2x minus 3 plus 2 times 2x minus 3. Therefore, my two factors will be 2x minus 3 and 3x plus 2. 3 over 2 will be one of my zeros, and the other will be negative 2 over 3, and the other zero will be x equals positive. Oh, I'm sorry, x equals positive 2. So I have all the zeros that I have. Solve completely for the zeros using the synthetic division. That's a lot better. So 2, 6, negative 17, 4, 12. Bring down the 6, 12, negative 5, negative 10, negative 6, negative 12, 0. So you get the exact same thing as from before. And then you can kind of copy and paste what you have factored from the previous because you're pretty much doing the same thing. So x equals 3 over 2, x equals negative 2 over 3. So these three will be my zeros. 2, 3 over 2, and negative 2 over 3. Based on the results, which of the following is true? X minus 2 is not a factor. It is a factor because I have a remainder of 0. 2 is one of the zeros. Check. Negative 2 is a complex conjugate. First of all, I didn't go over what a complex conjugate is, but I will eliminate that for your answer choices. That's not definitely true. Have 3 distinct zeros? Yes, because I have 1, 2, and 3. Distinct means different, unique. H of 2 is 0? Yes, because when you actually plug in 2 into the equation, you get a 0 for that. That's what the remainder theorem says. H of x is a multiplicity? Nope, I don't have any repeated zeros, so it should be B, D, and E for this choice right here. Halfway there, let's go to the next question. Use the remainder theorem synthetic division to find the zeros. Now, this is a power of 4th degree function, so it's going to take some time. So we're finding the zeros of this. So if I wanted to actually utilize what we know about the synthetic division along division here, we're going to go to our calculator once again, store 1 into the x, and start from scratch. So the equation here, it says 2x to the power of 4 minus 7 x to the power of 3 minus 12x to the power of 2 plus 37x minus 20. So then I'm going to plug that in. Oh, look at that. I get a 1 as one of our zeros. So we're going to shave off one of the layers there and then see what happens. So bring out the 2. This one, I'm just going to relatively go through it quickly. All right. So now I have 2, negative 5, negative 17, 20. That's another cubic polynomial that's stating 2x cubed minus 5x squared minus 17x plus 20. Now I want to find the zeros for that as well. Let's see if x still works for this. 2x to the power of 3 minus 5x squared minus 17x plus 20. Oh, wow. Okay, so I definitely have a multiplicity now because I have a repeated 0. Bring down the 2, negative 3, negative 3, negative 20, and that's 0. So it seems like I found all the zeros using the remainder theorem. All that's left to do is use the quadratic to figure out the rest of the zeros. Okay, so how would I be able to factor that? It seems like it's another AC method. So I'm just going to show you guys step by step. That's not 30. That should be 3x minus 20. So AC should be negative 40. Two numbers that multiplies is negative 8 and 5. So 2x squared minus 8x plus 5x minus 20. 2x, x minus 4. Plus 5 times x minus 4. So these two would be one of my factors. 2x plus 5 is remaining, so that's my other factor right there. So I want to find out all the zeros. So x equals 4, x equals negative 5 over 2, and then x equals 1, x equals 1. These 4 would be my zeros. What is a leading term and what does it tell you about the end behaviors? Well, the leading term is 2x to the 4th, means that end behaviors, as x approaches negative infinity, y approaches positive. As x approaches positive infinity, y approaches positive. It means that it's both going up like this because it's positive coefficient with an even degree function. That's how it should look like. So I have the end behaviors, both arrows going up like this. I'm going to plot the zeros, 4, negative 2.5, and 1. So here's how it's going to look like. Draw the arrows. It's going to go through at negative 5 over 2 because there's no multiplicity there. It bounces off at 1. And then it's going to come back down and it's going to hit the 4 because it goes straight to the 4 once again. There's a multiplicity of 2 here. Please keep that in mind. So you'll have a W shape like this. By the way, that's the food for thought. Your y-intercept here, it says that it's -20, the very last number. So it seems like we're right on the money. That y-intercept is somewhere in the negative zone. All right, number 5. So number 5 is a little bit of a tricky question where I gave you x to the power of 3 minus 17x minus 4. There is a term missing. That's the one thing I really wanted you to remember. So calculate one of the rational zeros by using the remainder theorem, it says. So I'm going to go to my trusty little calculator here. I'm going to store 1 as x, which is already stored in there. I'm going to type in x to the power of 3 minus 17x minus 4. All right, so 1 doesn't work. So let's plug in negative x and see if that works. That doesn't work either. So 2, hopefully that works. Negative 30, negative 2. That doesn't work. So remember, the factors of 4 is 1, 2, or 4, by the way. So you have to skip the 3. 3 is not part of your zeros. So let's plug in 4 into the x and see if this works. All right, so negative 4. All right, there we go. So negative 4 is the one that gives me a 0. Remember, we talked about the variations of the factors of the very last number. You're not going in order 1, 2, 3, 4, 5, 6. Rather, you're finding the factors of the last number and then plugging those in as your bait to catch the fish. So we have negative 4 as one of our factors. So we have 1, negative 17, negative 4. The trick here, guys, I am missing x squared. So it's best if you actually fill that gap up with 0x squared to help you guys out. If writing it this way helps you, please do so. But for your synthetic division, you cannot forget that 0. Otherwise, you're going to make a mistake. Bring down the 1, negative 4, negative 4, 16, negative 1, 4, and that's going to be 0, like we talked about. So this actually will give me x squared minus 4x minus 1. And calculating one of the rational zeros, we already found it. It's x equals negative 4. So based on your result of the quotient, what is the next step you must do in order to find the rest of the zeros? We have to factor the x squared minus 4x minus 1, but you guys can probably already guess that this does not work. It does not work in terms of factoring. You guys know better than that. If it does not work for factoring, it doesn't mean that you stop there. It means that you actually do the quadratic formula. So quadratic formula for this, negative b plus and minus. For the test, I am not going to make this to be this complicated, but if you run into a question where you can't factor things, it shouldn't really surprise you. You should still be able to use the quadratic formula and get your way around it. So I'm going to plug everything in. 4 plus and minus, 16 minus 4 times 1 times negative 1 all over 2. So 4 plus and minus the square root of 16 plus 4 over 2. 4 plus and minus square root of 20 over 2. This is the answer that we're going to type in into our calculator. So, because at the end of the day, we want to sketch this whole thing. We want to do 4 plus square root of 20 divided by 2, which gives me 4.236. And then we're going to do 4 minus square root of 20 divided by 2. That gives me negative 0.236. All right, so those two would be my solutions. Those two would be my zeros. And then we're just simply going to sketch it. So 4.236 will be right here. Negative 0.236 will be right there. And then the other zero we found out was at negative 4, so which is all the way over there. Now, with the leading term being x to the power of 3, it means that our n behaviors will go down and up. So, and our y-intercept, as food for thought, was at negative 4. So here's how it's going to look like. But I really don't care about this value, so I'm just going to erase the y-intercept. Here's how you're going to sketch it. Goes through, and goes through. I know that this is terrible, but imagine that this kind of goes through right there. All you have to worry about is the n behaviors and the zeros. There is no multiplicity for this whatsoever, so there's no balancing, no squigglies or crazy things like that. But the main bulk of it was this part 2, part B, where you're supposed to use the quadratic formula. Do not panic if you can't factor. You have to use the quadratic formula to get the zeros still. Last question, divisional analysis. We are going to see which one is better. Which one would be better to use for this, synthetic or long? The answer is synthetic. Why? Because look at your divisor. It's very easy. Negative 3, negative 5, 2. Uh-oh. Do we stop there? Actually, I also made a mistake. We're missing x squared, and we're also missing that last number, which is 0. So we have 0x squared. 2's x, and then 0 number. Then you put 3, -3, -9, -14, -42. This turns out to be really crazy, but 126, -124, that's 372. So that is going to be my remainder. And let's see, verify if this makes sense in here. So you can use your calculator to actually verify this for you. So I'm going to store 3 into the x as if I'm doing the remainder theorem. Then type in the equation and see if I get the same thing. Oh, there we go. So we get -372 as our result. So that should be our remainder, in which what we get is true. All right, divide the following. We want to use, obviously, long division for this because we don't have a simple divisor. We have x squared plus 2. So we have x to the power 4 plus 6x squared minus 3 divided by x squared plus 2. So the way that we are going to do this is that you're going to put x squared at the top just so that you can match the first terms together. That's x to the power 4 plus 2x squared, and then we're going to subtract them, 4x squared minus 3. Then what do? We put the plus 4 up there to match this. I'm sorry, that's 8. And so when you subtract these, you should get a -11 for this one. So our final answer would be x squared plus 4, which is our the result. And we got to put our remainder always over our divisor. Remember, it's negative because it's -11. So this will be my final answer. Describe as to why you decided to use specific division for part A and part B. For part A, divisor was x minus 3. Oh, sorry. Which means you can simply solve for the x. Solving for x is very simple. It is an integer. Integer means no decimal point. It is x equals 3. But B, if you were to solve for the 0 for this, x squared plus 2, you're going to get x squared plus 2 equals 0. Solve it, you get x squared equals -2. And when you square root that, I mean, just by looking at it, and there's a plus and minus, of course, that is a crazy number. It is an irrational number. It is an imaginary number. It doesn't exist. So you can't simply plug it in, or you can't do synthetic division with it. I mean, imagine doing synthetic division with the square root of 2. That is ridiculous. So it just makes the job a lot more difficult than it needs to be. So the divisor was x squared plus 2, which makes synthetic division almost impossible. Or actually, it is impossible. Because the zeros you solve is imaginary. Remember, square root of a -2, you can't do a square root of -2. Go to your calculator and see what happens. You're going to get an error message, right? Like this, you're going to get an error message, which means it's non-real. You can't plug in non-real numbers into and, finding multiplied numbers and things like that. So therefore, the reason why the part B, you have to use long division for it is simply due to that. Okay, so there's benefits as to when you're using long division and when you're using synthetic division. Please keep that in mind. So I hope this video helps and helping you guys understand what I am looking for in this particular chapter. You must study. You have to read. You have to watch the video. You got to go back and take a look at your notes. I'm going to make the test a little bit easier, like no quadratic formula questions. Definitely, you have to study the graphing and multiplicity. All that stuff is a fair game. Factoring, please brush up on that as well if you're not so comfortable with it also. Please feel free to shoot me any questions if you have anything. I'll upload this particular file of what I found out, all the answers up into the Teams. Besides that, I think that's all I have for you guys today. Thank you and good luck to you guys on Friday.